My name is Brian. I work at, I'm a senior software engineer at Couchbase, and I'm going to talk about high performance networking using eBPF, XDP, and IOU ring. Just a little bit about me. I work at Couchbase on the clustering and control plane component, and I'm interested into all things Linux, eBPF networking. I live in beautiful Santa Cruz, California, so I literally enjoy long walks on the beach. And one thing that I should note is that none of the content in this talk actually has anything to do with my job at Couchbase. I work on the control path stuff there at Couchbase. This is just sort of a passion project as well as a open source project. So who cares about networking anyways? Like, why should we care about any of this? There's probably a million answers. I mean, the most compelling answer that I've come up with is that networking, disk, all these I/O sources work as kind of like a fundamental bound to your application's performance. Obviously, you can never go faster than the physical networking of, you know, the box or server that you're on. You can't actually do that. I mean, you can make your application logic as performant, and amazing as you want, but at the end of the day, you're going to be bound by some of these fundamental barriers. And I just like networking, and so it seemed like there was a good reason to do it. So here's some history, just like a very quick overview of the landscape in networking right now on Linux. Our options kind of range from like the standard socket API stuff, you know, normal blocking sockets they're usually referred to. Generally, the request then kind of works in a one thread per request, you know, handling that sort of fashion. And then as you get a little more advanced, there's kind of async sockets, which would be like Epoll and non-blocking sockets. Basically, Epoll, you just register a bunch of sockets that you have interest in, and it notifies you when they're ready. So you can kind of multiplex the networking upon, you know, maybe you could have many requests or many sockets per thread. And then there's IOU ring, which is new. I'm going to probably go a little more into that later. It's sort of the kind of the answer to some of the gripes that people have had, specifically with asynchronous disk type stuff, but it also works for networking. And then there's kind of lower level stuff. There's like the AF packet interface, which also is kind of like a blocking interface, but gives you access to like layer 2 frames directly. You can also get layer 3 packets. And then there's like the most advanced kind of crazy stuff that there is, and this like kernel bypass. And so DPDK is probably the most popular one. There's also Netmap. So eBPF is a revolutionary technology with the origins in the Linux kernel that can run sandbox programs in an operating system kernel. It is used to safely and efficiently extend the capabilities of the kernel without requiring to change kernel source code or load kernel modules. I read that word for word because I just thought it was a very good explanation of what eBPF is. I just wanted to kind of put that out there. So the majority of this talk is going to talk about XDP, and then also kind of my journey in building a high performance, you know, AF-XDP adapter for an existing Rust asynchronous runtime. But again, with a little more history. So for a long time, AF packet has existed. It's kind of been it's been okay, and people use it sometimes if they want to do really fast like packet captures and things like that, but it wasn't particularly heavily used. And they were coming up with a new version of it, which they were kind of dubbing AF packet v4, and at the same time eBPF was kind of coming into existence, and they were starting to look at it for networking use cases. And basically, they decided to make it, instead of, you know, putting out AF packet v4, this is the Linux kernel devs, of course. Instead of releasing it, they kind of transformed it into XDP. And I'll go into exactly how that works and what that is. But basically, an XDP socket uses eBPF to route packets directly to user space. And so this is kind of where the more interesting stuff comes in. So XDP comes in two variants. Basically, there's a standalone variant where you basically write it's the equivalent of a callback. They're written in C and compiled to eBPF bytecode using LLVM. And basically, it's an event-driven model. So it's ran on every packet as it's received. Then there's AFXDP, which is kind of the way to get packets directly to user space as quickly as possible. But it uses the same underlying technology. It's using the same, tools. So Linux kernel networking, the general stuff is great, but there's a lot of use cases where it's not ideal. It's relatively scalable, but at some point you're kind of at the mercy of whatever the kernel wants. There's sometimes a lot of copies involved with a network request. It can be hard to really get full line rate performance out of it. And especially with latency, you tend to have issues controlling exactly where, how much latency there is and, dealing with that. Speaking of P99s, right? So my use for XDP and how to use XDP in general. So what I wanted to do was design a AFXDP backend for a library called Glomio. Glomio is kind of a IOU ring focused asynchronous library for Rust. There's a lot of async libraries for Rust. There's some very big popular ones. Those are great. Unfortunately, they were kind of slow on picking up, things like IOU ring, and they generally just sort of have a design that I'm not as interested in. I'm definitely more focused on a thread per core model. Those tend to use like an end-to-end kind of scheduling system. This adapter is being worked on currently. It's on a forked version of Glomio. It's not currently merged. Definitely would love contributions if anybody is interested. So the main question I have is, how would you design something like this? And so first, let me give you kind of the basic layout of AFXDP specifically. So you have a hardware queue on the top left here. This is a NIC hardware queue, right? So like this is where the packets actually go. And like high performance NICs will have many of these. Some NICs only just have one. But generally speaking, there can be a lot of these in a high performance NIC. And so you attach the AFXDP socket to that. It requires a UMEM, and then there's also some other ancillary stuff that I'll explain. I'll just touch on what they are and then talk about what they're for. There's an RX and TX, so receive and send rings. They're basically queues that are used to pass frames from user space to the kernel and kernel to user space. And then there's some rings that are attached to the UMEM. The UMEM is a uniform kind of memory region. It's just basically a big block of memory that you pre-allocated. This is kind of following the same model as something like DPDK, which will pre-allocate all the memory. Generally, you don't want to be allocating memory when you're receiving packets. And two rings are attached to that, the fill and the completion. And I'll kind of go into what those are. So these are all ring buffers that, pointed out right here. I should note they're all single producer, single consumer. That'll become interesting later. So here's the basic layout again, except I've added something that kind of makes it the more realistic representation, because all this happens on the left normally in kind of one core. But the actual driver code, generally speaking, if you're using the needs wake up type of notification for this, which I'll go into a little bit later, means that the actual driver code happens in another thread. It's basically IRQs will be fired when packets get there, and then the driver will process them. And then the left side here is only actually reaping those, so to speak. And so even though it seems like it's a single core process, actually you're dealing with 2 cores worth of stuff. And you can combine like many of these AFXDP sockets on different hardware queues, and then kind of all have them be handled by a single IRQ thread or whatever. But it's definitely something that should be noted. Here's some code. This is like the default eBPF code. And so first thing you do with eBPF code, so this is C code. It's a subset of C, so it's like a very simple subset of C. And you create a map. This is what's going to hold the actual AFXDP socket entries. And then you have a little program that you create here. And what happens is you look up which queue that is supposed to go to, and you redirect the packet to it. Something I'll point out here is that if you look closely at this code, it's pretty clear how you could modify it to maybe do other interesting things. I don't know, sharding comes to mind. Definitely distributing packets in sort of like a uniform fashion. Maybe you split all of the your requests based on keys, so you could do sort of a split thing and then send it to the actual AFXDP socket that is handling that range of keys. So there's a lot that can be done here. I mean, the ability to program the kernel is a powerful one. So here's a few other designs that I kind of looked at when attempting to build this, and one of them is like a shared memory region and many sockets. Threading here can get a little more complex if you start sharing the UMEM. All these queues are single producer, single consumer, meaning that only one thread can access them on each side. And so if you're contending for the same stuff, you start having issues and you start needing to use locking. Here's another design. This is a kind of what I'm calling the segmented design, where you basically break everything per CPU. They have their own AFXDP socket and UMEM. And this is sort of, I'd say this is the closest to the design that we ended up sticking with. Glomio is a thread per core designed runtime. And so basically it just made sense to keep everything kind of all in the same core. Now, there is also a way you could probably share the UMEM across many of these, and then what you do is segment the UMEM so that you don't actually contend over the same stuff. But even that can get complicated, especially when you're dealing with the fill and the completion rings. To give a little more kind of description to what the different queues do, because this whole thing is basically a matter of passing things back and forth, and so the queues work for that. So like here's like kind of an example of what some of the code would look like. This is in Rust. This is sort of just an example of like how easy it is to interface with it. There's definitely a lot of directions I could have gone when designing this. Definitely took a lot of inspiration from stuff like C Star and that use DPDK and stuff like that. So basically, interfacing with the kernel is easy. There's a library called libbpf. You use it, you can call its functions, and what this one's doing is pretty simple. So basically, you look at how many items are currently in the queue. You grab those items in the queue, and then you just release them, which is basically tell the queue, we took those things. And so interfacing with these queues is easy. The queues are fundamentally simple, and so basically the main flow in a normal AFXDP program would be you add things to the fill ring. The fill ring is what tells the kernel that you you want to start receiving packets. And so you give it a chunk of packets that it can start receiving data on. And then you read the RX ring, which is the one where you receive data. Then you can utilize it in whatever way you'd like. And then let's say you want to send something out. Then you would put it in the TX ring, and then once those are finished sending, you grab them from the completion ring. So it's basically like you're just moving things around from place to place. So it's actually fundamentally very simple, and it's part of the reason why I decided to go with this instead of something more complex like DPDK. DPDK is an amazing program and library, but it's complicated, and it definitely a heavy dependency to bring. So I kind of want to talk a little bit about like how this fit into the larger framework. So Glamio was a runtime that focused on IOU ring. And so when integrating, there's like a few different directions that you could go. Basically, one of the issues, one of the things you need to think about is, first of all, there's multiple different modes that you can run in. So with AFXDP, there's kind of the first mode that was created was called needs wake up mode. Needs wake up mode basically means that you have to call certain kernel syscalls. So basically like poll or send to kind of notify the kernel that you want to keep receiving stuff or that you want to send something out. So that was kind of the first one that existed. This integrated pretty easily with the existing setup because what I could do is just basically put those poll requests into the IOU ring queue and then be off to the races and be notified when something actually happens. The more complicated one would be busy polling. So busy polling is a technique that's used in high performance networking all the time. So like DPDK is fundamentally a busy polling framework. It uses userspace drivers and just spins the CPU as fast as possible. So for busy polling, you just make the calls in the runtime loop and you can't easily sleep or block. So this is a little bit more problematic unless you want to be spinning all the time, which is an option, I suppose. So basically this option is kind of the nuclear option. That's how I'd say it. It makes it harder to use existing capabilities of IOU ring. You basically have to create your own mechanism for notification of the rest of the runtime stuff. You can't just fit it, plug into the plumbing for all that. But it's also fundamentally the most powerful mode that you could use. Basically, this mode the busy polling mode moves the IRQ handling and the driver code into your actual syscall. And then what you do is you call poll actually, and when you do that, you're actually calling directly into the kernel's NAPI loop and receiving the packets directly from the networking driver. So this means that we would be able to get rid of that other thread that was sitting there handling IRQs and stuff like that, and maybe get better density in our runtime. If you figure that you've got 10 cores, you could actually fill maybe at least most of them with workers actually handling requests. There's a few other considerations. Is relying on the IOU ring for needs wake up notifications, readiness too slow? It hasn't seemed to be the case, but does it add too much latency instead of just calling a blocking poll right there? My tests have shown that this is not the case, but it's definitely something to consider. There's also a new feature coming out for IOU ring called multi-shot poll, which is a fascinating feature where basically you set up a poll request and if it fires, that doesn't mean it disarms it. It actually just keeps firing every time something, that event happens. So you don't have to keep resetting it, essentially. And another consideration is that the runtime is cooperatively scheduled. So how does this guard against like tight loops on the receive, on like the receive function for when you're receiving packets? Most of the calls to libBPF are actually synchronous. Is that a problem? This is something that's kind of still in the somewhat unknown. Largely, it doesn't seem like it is, but fundamentally it could be. I mean, there's no reason why if you're in busy polling mode and you enter into actual driver code, I mean, there's no reason to say that something wrong couldn't happen. But I suppose, you know, that could be said about most things. So this is all a work in progress. I would love contributions. Work on it over. There's the link to the main repo, parting words. I didn't get a chance to talk about IOU ring too much, but if a lot of this sounds too complicated or, you know, just unnecessary, I would recommend at least using that. It's, you know, an amazing interface and definitely the future of most users async IO on Linux. And that's it.